Hello, welcome. Thank you. Equivalence partitioning seems a bit loud, does it? Equivalence partitioning and boundary value analysis are techniques that have been around for many, many years, a bit like me, really. They are simple techniques, they are easily taught, and they're applicable in many different situations. But because they've been around so long, it's surprising they're not used more. In the experiences I've had, in the companies I've been in, they don't get used anything like as much as could be justified to use them. And where they are used, they're not used very thoroughly. I was kind of blown away when I first got into testing and learnt these techniques, because suddenly a massive, great big problem called testing had become a much, I won't say a much easier, well, it was a much easier problem than I'd originally sort of looked upon it as. So why is it that these techniques are not being used? Is it because they're so old, they've gone out of date? Is it because new modern techniques have taken over? Or is it that the software has changed in ways that makes them no longer relevant? Well, the simple answer is no. No, these techniques are as relevant today as they have ever been, perhaps more so, because one of the primary goals of the technique is to reduce the amount of tests that you need to run in order to gain that required level of coverage or competence or whatever you're aiming for. So in this presentation, I'd like to sort of persuade you to share with you some of the facets, some of the parts of these techniques which are often overlooked, but that make them so much more powerful. I'm going to start with a quick introduction to the techniques and give a simple example. Then we'll dig a bit deeper, look at some of the facets of them, and if we've got time, we'll look at the relevance of the three-value technique. So, equivalence partitioning, it's really about identifying behaviours of the software that are different, and then testing each one of those behaviours. So it's recognising that a given set of inputs will produce a particular behaviour of the software or cause the software to behave in a particular way. So different ways that the software behave are caused by different inputs, but not every input causes a different behaviour. So we don't want to test several of those inputs which all cause exactly the same behaviour, because we're not testing anything different, we're just testing the same thing again and again. With equivalence partitioning then, what we're trying to do is divide or partition, hence the name, equivalence partitioning. We're trying to partition, to put together into groups, ranges of input values or groups of input values, output values and other things into sets or partitions or subdomains. There's lots of names for these things. But what we say is that all the values in that particular set or partition will be treated equivalently in the same way by the software. So hence equivalence partitioning. We are trying to identify those things which are going to be performed on, acted on in the same way by the software. By doing this, by considering the inputs and the outputs and other things besides, we can explore lots of different behaviours of the software. The assumption is that we're going to test one value in each group, and if that value works, then we will allow ourselves to assume that all the values in that group will work. So we don't need to test them to make sure. Rather, we just pick the one value, test it. If it works, great. If it doesn't work, well, we can assume that all the other values probably won't work either. You know, there's a defect that needs fixing, so let's get on with it. It's much better to choose one value from each partition that we're interested in than just not thinking about this and doing several tests, several of which may exercise exactly the same behavior of the software. So as an example, consider a program that accepts an integer value in the range 1 to 100. Now with that specification, I know I've got 4 partitions. The first one is all values in the range 1 to 100. We know that this program, whatever it does, and we haven't gone into that part of the specification yet, we know that this program is meant to accept and process numbers in the range 1 to 100. We don't know any more yet, so we can't break it up further. But what we can identify is that there are 3 other partitions, 2 of which, all of which are invalid, 2 of which are either side of the valid partition. So numbers 101 and greater should be rejected nicely by that program. Numbers 0 and below should be rejected nicely by that program. Now you might say, well, that's the same behavior. Yeah, it depends. It could be a different behavior if the message is different. You know, your number is too low or your number is too high, for example. The 4th partition is everything that's not on that blue line, where the blue line here, sorry, blue line, grey line mark, that line represents all possible integer values, so up to plus infinity and down to minus infinity. But anything that's not an integer, I'm going to put into this partition here. It's invalid. Now, you may be thinking, well, hang on a minute, Mark. Alphabetic input would be different from floating point numbers, 1.6, as opposed to ABC or Control F or function key 3. Yeah, if you've got some concerns about all those different types of inputs, then yeah, let's have other partitions. But I guess most of them, if not all of them, will be invalid. So we need to, decide whether it's worth doing that. Are we going to drill down into that depth? And that's something we'll come back to later. So as a couple of examples, here's some bank interest rates. Dealing with paying our interest, perhaps on money that's in the bank, we would be affected by the interest rates, which are in turn affected by the balances. So we'd want to check that the interest rates are calculated correctly for each of those bands. One test will do it from each partition. So our partitions can have the adjacent valid partitions. It's not all about numbers, though. It's not all about numbers and ranges and so on. Here we've got types of membership for a sports club, is what was in my mind when I was writing this. These people are individual members. If you've got one of this title, you're a single person. But if you're a couple, then it's a joint membership, or if you've got other people, if you've children, then you have a family membership. So the number of people is different. You could have a different set of partitions for the same data. For example, if they pay or not. Do they have to pay for membership? And I would suggest perhaps the staff and the honorary do not pay, whereas everybody else does. So we're partitioning this information, this input, or the data, depending on how the software will process the that data. What the purpose of the software is. Boundary value analysis is the other technique, and it's based on the same model of the software. So it's a good technique to look at because it's looking at the values at the edges of the partitions, or the boundaries, of course, those boundary values, because we're looking for the case where it's just off by 1, typically. The maximum value in this partition gets treated as though it's the minimum value in that partition. These are very common mistakes because the programmer's never quite sure. Do I go round that loop x times, or is it x plus 1? Oh, it might be x minus 1. I'll go for x, and it should have been x plus 1. So it processes all the values except the last one, or an extra one if it's gone the other way. So defects tend to lurk near boundaries. They're easy mistakes to make because it's a difference between a greater than comparison and a greater than or equal to, and we can just get the wrong one. So it's a good place to look for defects. We should test values on either side of each boundary. Yeah. So again, with my program, which accepts an integer in the range 1 to 100, 1 and 100 are obvious candidates. They are the valid boundaries. And then the invalid boundaries are 0 and 101 in this case. So on to a simple example, and this is really simple, but it does highlight a few interesting points. It's a program that calculates the number of days until Christmas from some given date. The dates can only be from the 1st of June. That's so we avoid February and the number of days in it to keep the example simple. The inputs to the program are two integers, just two separate numbers representing the month and the day of the chosen date. So if we look at month, then we will have from the 1st of June, so that's month 6, to December, of course, where Christmas is. So 6 to 12 is our valid range. 5 and less, 13 and more. Now, drawing partitions in this way is a great way to sort of communicate the idea en masse, but not always the most practical way in reality. So we tend to suggest using a table like this. There are other tables too that are possible, and we'll show another one later on. Here we're saying, well, okay, for month then, we've got the valid partition of 6 to 12. There are invalid partitions, and of course there's usually more of these than anything else. Less than 6, greater than 12, non-integer. And we may want to break that up into others as well, possibly. The valid boundaries, 6 and 12. The invalid boundaries, 5 and 13, but also 1. Was anybody expecting me to put a 1 there? Because month 1 comes after month 12, but digit 13 comes after digit 12. Which should we put there? Who cares? We've thought of both of them. Let's put them both down. Now at this point, we're not saying we're going to test these values. We're just saying, ooh, they're there. Later on, we want to. When we come to choose design our test cases, we'll need to choose which partitions and which boundary values we're actually going to apply or test. The partitions for the day in this example, this is where it's a little bit different because 1 to 30 are valid for all of those months we've chosen. 31 is only valid for some of them. So 7, 8, 10 and 12. Again, in this table, I've been a bit lazy here. I haven't sort of said for month 9, 11, 6, 9 and 11. That's it. It should be 6, 9 and 11. Just to clarify when these are applicable. Oh, sorry, no. Stupid me. No, they're applicable for all of them, aren't they? Sorry, ignore me. Right. So less than no rocket science here. I mean, it's fairly simple and straightforward. Okay, and then the output. We can partition the output too. And this is where I've been a little bit simple. There are 207 days from Christmas until the 25th of December, which is when I traditionally celebrate Christmas. But if you're in Scandinavian countries, they do it on the 24th. So there's already a problem with the specification. Who knew that? So anyway, I'm assuming what day Christmas is on, and that's the correct thing. But of course, what happens on Christmas Day? What happens on the day after? Now, this is a sort of techie solution. Christmas minus Boxing Day is -1. Not probably what the end user wants. Now, I know you're thinking, well, of course, there's not an end user for this rather simple program. I was in Finland some years ago. I happened to be checking out of a hotel on not on Christmas Day, on my birthday. Much more significant to me. And as the person was checking out, suddenly I heard the music to Happy Birthday. da 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 da. And the receptionist said, "Oh, happy birthday, sir." Now, I'd actually forgotten it was my birthday. It was just another working day. Oh, right. So someone had, I've got a loyalty card with that particular hotel chain, and they've got my date of birth, so, they worked out it was my birthday. Isn't that sweet? Really nice. So, yes, it probably should do something different on day 0. When the output's 0 on Christmas Day, and it should probably then do something different again, -1, -2, up to -6. But let's not think about that too much. It would be an obvious partition to put in there. So this is what we have so far. We have our month, our day for the different ranges, and the number of days. Output, that is. So we're building up this table, and it's an easy table to communicate lots of great ideas, and better still, get more ideas from other people. That's one of the powers of this technique. If we just bothered writing a few thoughts down in terms of what partitions there are, what boundaries, somebody else might come along and say, "Oh yeah, but when that input hits this value, there's another piece of software which kicks in and does something wonderful." Oh, right, okay, let's make sure we test that as well then. It's really a powerful approach. We don't need to document it formally. You can write this on the back of an envelope and still achieve that benefit of getting other people to review it. And just to complete it, we're tagging each of these cells, because each cell represents a test condition. A test condition is something that we may wish to test, or we may test, or we may not. The importance of any one of these, or sets of them, is yet to be decided. So, let's dig a little deeper. Equivalence partitioning and boundary value analysis, when you work them together, they tend to be known as domain testing. The focus is usually on the behaviour of the software, but that doesn't mean to say we can't take a sneaky peek at take a look at the software itself, particularly if you're doing unit testing or component testing, where you've got access to the code. You'll find out more information which we can use to develop more detailed and perhaps more accurate partitions. But if you're developing from a system testing point of view, you probably don't have sight of the code, but you're thinking about the behaviour of the system as a whole, whether it's doing reasonable things. I can highly recommend to you the Domain Testing Workbook. It's a huge book. It is really work just carrying it, never mind reading it, but it's a fabulous book on domain testing. So if you really want to get into it in a big way, we talk about equivalence partitions. They're the same thing as equivalence classes, as domains or subdomains, and equivalence sets. As for notation I'm using, if it's a line with arrows on the end, it sort of goes off into infinity in either direction. We've got a range of numbers there, so that's an ordered set of values. Okay. I've got these little lines in, they're the boundaries. Now note that the boundary doesn't have a number associated with it. This is in contrast to some other people's views. Some people would put perhaps 0 up here, and then have 1, 2, 3. But the trouble with it is it's ambiguous, because you don't know whether that boundary value of 0 belongs to which partition. So I'd like to keep it clear. So each of these ranges of numbers within those sets are then our equivalence partitions. The values against the boundary are the boundary values. So again, there's 4 of those. And rather than write out all the numbers, we would be shorthanded and do this abbreviated version. And if you've got something that's not a range of numbers, then we represent it that way, or at least I do. So, equivalence partitioning, step 1, divide all the values of a data item into subsets or partitions. Now, we're, as I say, perceiving that all the values in one of those subsets will cause the same behaviour of the software. if there's any doubt, it's probably a good idea to split the partition to make a distinction. We believe that the values exercise the same code. I say we believe. We're not going to go in and do a formal proof of this. We're just going to say, well, yeah, I think that's the same, so we can just test one value. This is where the beauty is getting somebody else to review that then, because they might know something that you don't. If one value reveals a bug, they will all reveal the same bug. That they should all fail, but they're not going to fail in any different ways. We don't need to test more of them. One value, if it succeeds, then they will all succeed. We don't need to test the others to make sure. This technique is giving us permission to say, no, just the one, move on, get on with it, reduce the number of bugs. So we need only test one value. Valid partitions give us our positive testing. We are doing, inputting stuff into the software or making it do things that it's meant to do. It's useful for it to do. Whereas the invalid partitions are the negative testing, and there the values typically should be rejected or should be impossible to output if we are partitioning output, for example. A few more examples here. Transparency input 0 to 100, quantity of an item ordered. This is where the 0, I've got a question mark there. Is that going to be valid or is that going to be invalid? It depends on the software, the context at the time. It may be that you're ordering up numbers of other things, so having a 0 could, or might be you putting 0 in to delete that thing off your shopping basket. Here, we've got no arrow on the end here because this is a count of things. It's the number of characters we're entering into an input field. I defy anybody to come and enter -3 characters. You can't do it, I can enter 0, i.e. not enter anything, or I can start entering characters. But you can't, the delete is just another character. It's not a negative character. So that's where it gets just that little bit different. Step 2, well, select a representative from each partition. Select a representative from each partition. We only need one. Be brave. Just choose one and move on. If you have any doubt about the other partitions, then we need to split it. But you only select them from partitions that are of interest. This is another mistake that I see made. Once people have identified lots of partitions and boundaries, they set about testing them all. All? Why? There's usually loads of them, and we can get a better feel for the software without testing them all. Test the ones that are most likely or those which are of greatest risk, perhaps. So the strategy would be, do you want to build confidence in the software, then go for those typical values. Go for the usual scenarios. What values would users normally use? That's the best thing to do there. And you go inside the partition. If you want tests that find bugs, so you're just after finding lots of bugs, and possibly risk-based, so you're finding the most important bugs, then we need to select boundary values, because that's a good place to go for looking for bugs. So the benefit of the technique is it reduces the number of tests. It cuts down massively the number of test cases that people would otherwise generate, because they think, oh yeah, we need to test this. So if I've got a program that calculates the square root of an integer number, they might say, oh yes, I'm going to test 10 and 15 and 25 and 47 and 58 and just go a whole load of numbers. But why? We only need test 2 values. 9 because its output is a whole number, and 10 because its output isn't a whole number. They're the 2 partitions. Then you might consider the boundaries as well. So, typical partition values are good for regression tests. When you are wanting to build confidence, then that's kind of what regression tests are about. So if you can build a whole set of regression tests based on the valid partitions where you've chosen typical values, you're onto a winner. Extreme unusual values are better at finding bugs. That's the boundaries. And if you get that feeling, I must pick one more value, I've got to test 2 or 3 values in this partition, then what you're really saying is that this isn't one partition. It's, it could be 2 or more partitions, and we need to perhaps recognise that. Maybe that's the time to go and talk to other people. What do you think? Go and talk to the developers, see whether it is really the case. So, boundary value analysis, it's using the same model, so the 2 techniques are related. They're like brother and sister. I don't see any point in using one of these techniques without using the other. Yeah. We want to select the boundaries from each ordered partition of interest. Sometimes the boundaries are not really of interest, minimum, maximum value, but sometimes they can be very critical. So not all partitions have boundary values, if it's a set of titles, for example. Not all ordered partitions have 2 boundaries. Often we don't get an upper specified limit for certain inputs. The inland revenue systems, the government systems in the UK, many years ago, had a problem when Elton John became popular, the rock singer. Because he was earning so much money, he crashed their system because he couldn't handle the amount of money going in as his wage or his income, whatever. Because nobody has specified what the upper limit for salary should be, and that's where we need to think. And in fact, this is where as testers we need to sort of put on our thinking caps and say, well, what should really happen here? Because somebody should have asked that question. I mean, it's the experience versus the specification. The spec says it's a number of items to be ordered, and obviously 1 is the lower limit. 0 doesn't make sense unless you're deleting something, perhaps. But what's the maximum number of items that can be ordered? A catalogue company in the UK discovered they had advertised the price of a television set as £3.50. I can't translate that into rubles, sorry. It's not very much. And it should have been 350. The decimal point was 2 places in the wrong place. They didn't realise until people were ordering truckloads of televisions. So wouldn't it be sensible if the system, we had some sort of limit somewhere that said, well, once you get to 10 televisions, we ought to stop and ask some more questions, because it's not often you're going to get people ordering loads and loads of televisions. Different ways of partitioning one item. These are known as dimensions. This is where we can get a greater richness into our testing by thinking of these things in different ways, not just the obvious input field. So an input could be an input to a name field, for example. So we've seen that before. Yeah, the number of characters that are in that name. The number of matching characters. Depending on what operation is being performed, how many of those characters, when we're searching for that name, are we going to match against, or do we match against, if that's appropriate to the functionality? Which characters, not just A to Z, but all the national characters and so on. And then others, whether there is leading or trailing white space, which in theory shouldn't affect the input, but often does. Non-printing characters, null characters, wildcards, lots of other things. Now, some of these things here, this is the detail which would be ironed out at the development stage in component testing or unit testing. But we shouldn't be doing that necessarily at the system testing level, unless it hasn't been done earlier. Types of partitions, the things we can partition. Well, the input we've talked about, the output we've talked about. What about the data itself, the names in the database? If you're buying stuff from a store, you're testing the online purchasing system, we need to have the whether items are in stock or not. So it's how much data is in there, how many records are in there. Yep. The internal or intermediate results. From the input to the output of a program, there's lots of data that gets stored at some intermediate stage, typically. So we might think about what would happen, what might be stored there, and what are the upper and lower limits for those, and the format of the data, and so on. What can we do to stress those out? Then the environment, configuration aspects, and time-related partitions, the order of events, for example. When it comes to identifying both partitions and boundaries, not every partition has a boundary. That's kind of a list. I'm just going to show an example of the last two here. The relationship partition, I kind of like. Most people miss it out. They look at literal values. But here we're saying, well, what's the relative value of this compared to something else? Is it smaller than that? Is it the same as? Is it larger than? So the tester's salary should be greater than the developer's salary. Yes. Well, I think it should. I'm not saying it is. The end date of the insurance policy should be later than the start date of the insurance policy. It's kind of, well, yeah, but if you put it in the wrong way around, will the system still carry on as though it's not wrong? The loan amount needs to be less than 75% of the salary, or some other calculation. It's making sure that we're in that partition, even if it's a variable partition, because it depends on other values. And talking about depending on other values, we might have a situation where we're trying to sort of say, well, is the credit card valid or not? Well, it depends on a combination of values. Now, we can test combinations of valid values, no problem. When it comes to the invalid ones, we might need to test each one separately. It's more expensive, but it depends on how the software works. If it just reports the first error it finds, or does it scan all the input fields and say, right, that's wrong, that's wrong, that's wrong. Depends. The other issue we come across is the open boundary. I was saying before with the television sets, no one's specified an upper limit. In this example here, it's the upper limit for the age of a driver. Now, you usually enter the date of birth for a driver, I would imagine, and then the system works out his or her age, and then calculates the premium accordingly. Now, I've no idea. Happily, I haven't got there yet. But I perceive that insurance might go up, but I think it might actually go down. I'm not sure. This is rather optimistic in that it's not coming down. It doesn't come down as that fast. I'm discovering with my son's insurance. Anyway, what do you do if the specification hasn't been, if the spec doesn't say, well, perhaps we should still test some upper limit, some reasonable limit. And the story associated with this is a guy in London who had an accident with his Rolls Royce, and the policeman said, "Can I see your license, sir?" And he said, "No, I haven't got one." Because he was so old, he was 95, and this is a few years ago, but it was before licences were thought of for driving, so he was legally driving without a licence. Anyway, he was 95, so that was in London. I'd do that myself. Set your boundary beyond some reasonable end and test that. Investigate physical boundaries. I mean, how many characters can you enter? So if it's going to be displaying an age, is it only showing a 2-digit age, for example? Investigate similar limitations elsewhere. Where else in the system do you have this kind of data? Yep. Documentation, that's what I've been using in the previous slides. This is a different form inspired by Kemkana. Valid partitions, invalid, boundaries and special, and then notes, which could be really useful, adding notes. Other people have added risk information in there, whether it's high, medium or low, that sort of thing, which can be useful. Where you need documentation, where you want people to review the ideas, for other people to learn from what you've done, and for auditing purposes and reuse. You don't have to partition customer name every time you come across customer name. You do it once and just reuse the table. Much more efficient. Right, the 3 value, I'm running out of time, so I'm going to just skip over this. But the bottom line, by all means, have a look at the slides. And if you have any questions, I've booked a session. I think it's about 4 o'clock in the discussion room. It's around that time. So you could collar me there or any point in the conference. I'm around all day. Or send me an email or something afterwards. But the 3-value BVA is described by ISTQB and this other standard here. But it's completely and utterly flawed in the sense that, I mean, basically it says you take 3 values, the boundary value on one either side, and you have to identify all those, and then you reduce it to the minimum. Why? The other aspect is it's identifying then 1 and 9 as boundary values. But what's the difference between 1 and 9 when they're in the same partition? Nothing. There's no difference at all when they're in the same partition. It's not 8. So we don't need to test both of them. We only test one, and that's called the equivalence partition value. So you just take equivalence partitioning. Sorry, this is the logical proof, as it were. What the developer can do, only one is right, and they can also do that. So, yeah, I'm not going to attempt to try and explain that, but hopefully it's clear. So my conclusions then. These are oldies but goodies. A lot like myself, I like to think. They're still relevant and useful today, even though they've been around for many, many years. The first book on software testing was The Art of Software Testing by Glenford Myers, published in '79, I think, and he talked about equivalence partitioning in there, as if it had been around for a long while, and it perhaps had. So, it has been around. It enables us to see the wider picture if we consider those other dimensions, not only just inputs but outputs and internal states and the timing issues and so on. They're sharp tools, use them wisely. Don't allow people just to identify loads of partitions and boundaries and then test them all because they think they have to. Let's be more intelligent, let's select the important ones, but allow the techniques to find lots of conditions. I always say that if you're testing every test condition you think of, you're not thinking of enough. You've got to think of loads of things and then pick the best ones. So you always test the best test conditions you can find rather than just the first few that you think of. Yeah. So, and these tools, these techniques are just that. They are really sharp tools when used well. So use them wisely, assess the results and retune. Yeah. I think they're cutting edge still today. Thank you very much for listening.